Hello, everyone. Thank you for joining us today in this new Rhino User Webinar. I am Guillermo Varela from Magnet Europe. I'm here today with Mattia Bressanelli from TECNESYSTRA. He will show their computational modeling workflow of existing tunnels, which have challenging geometries using custom-built Grasshopper components. Mattia is a building engineer focused on computational design and software development, and he is the research and development lead at TECNESYSTRA Advanced Tunneling. Remember that in the last 15 minutes of this webinar, we will have some time to answer any questions you have about it. So you can ask them in the chat and we will check them at the end. Also, I would like to mention as always that we are recording the webinar and it will be available on our YouTube channel tomorrow morning, I hope. And I will send you an email when the recording is available, so no worries if you miss a part of it. Just to finish, thanks again to Mattia and TECNESYSTRA for the interest in presenting this webinar. And please start with the presentation if you're ready. Thank you.
Right. Thank you for the stage. Let me share the screen with you. All right. Okay, you should see the screen.
Yeah, it's working now.
Fine. Okay, so just a couple of words about the company. So TECNESYSTRA is a company. It has 3 years now. It was born from 2 other companies, Tecne and Sistra. Tecne is an engineering company of the Autostrade per l'Italia group. They handle all the highway infrastructures in Italy. And instead, Sistra is a geotechnical engineering firm, globally present. So we are about 40 people here in the Turin office. And we mostly deal with tunnel assessment, which is the process of renewing existing tunnels when they reach end of life or they need intervention for some structural reason. So the main problems with tunnel assessment is that we have a lot of data gathered from survey, and we have to handle it, and that generates complex geometries which are hard to model. And there are no real standard procedures to do that, as in existing tunnels. So we have to define our own workflows to do that. And the other problem is that, of course, most related to design is, of course, tunnels are quite old, and we have to intervene on tunnels which are open on the existing highways. So optimization and speed of operations, it's certainly a key detail. So having detailed models and detailed information in design makes for better construction sites. All right, so let's see the workflow, which we will see together today. It's like summarized by this flowchart. So we start from vector and point cloud data, which is usually gathered by a topographer, which is an external contractor, and it gives us a vectorized survey in DWG or any CAD format, and then a point cloud in PLY or LAS or something like that. And from that, we have to rebuild the tunnel, the existing tunnel. So we build the intrados mesh, the part that you can see directly from the point cloud. We extract the alignment information by processing the CAD data. And instead for the extrados, we can't see that. So you can't survey directly. So we have borehole data that is taken with video tools. So they like to do boreholes in the internal lining, and then with video they see the different layers that you can close between the intrados and the extrados, so we can build an estimate of the surface of the extrados. At the moment, we're doing that in Leapfrog, which is a geotechnical modeling software. We are moving it. We will probably move it to Grasshopper as well for the rebuild of the surface using GeoPy. I don't remember exactly. There's a library for geological processing in Python that you can integrate in Grasshopper, but at the moment that is done in Leapfrog. And then we also have from survey, the vector survey, the information about the road, so the different lines and sidewalk characteristic lines, and we can use them in Grasshopper to rebuild the surface of the road, which is then cut with the intrados of the tunnel as well. All right, so the first thing, we'll see tech demos then directly in the software, but let's just see a small overview with slides. So this is basically the script. We have a bunch of components built There are clusters at the moment, so user objects saved in a custom toolbar. We get the introdos arcs, and we use them to get the top of the crown, and then connecting the top of the different crowns, we get the alignments of the existing tunnel. That is done automatically in a couple of seconds. And then we can take the polyline and then split it into an horizontal projection and in a profile and build a land XML. So you can use it in other tools like Civil 3D or any other application for processing infrastructure data, or directly within Rhino with the custom tools we built. All right, then we build the custom, the introdos from the survey. So we get a very dirty point cloud with sometimes even cars and systems in it. We have to clean it up. So to do that, we take the vector data and we create a rough mesh in Grasshopper that is basically a loft of the crown sections, and then we use that in Cloud Compare to compute by distance, to filter by distance the point cloud. We'll see that later on. And then we get this mesh, we can extract it, put it back in Rhino. Usually we go with a 15 centimeter resolution, but you can choose your own. And then after we have this mesh, we go to the extrodos. We won't see this extrodos parts today, so I'll just mention it in the slide part. So we have a model in Grasshopper of the introdos, and we can use some tabular data. So we get some data in Excel, which is just information about the different layers and the position in the tunnel, and then we use that to build points around the introdos of the tunnel, and then those are moved into Leapfrog, and Leapfrog is basically doing an interpolation of these points to build a rough mesh of the extrodos, which then we can import back in Grasshopper. So this is the result we get. Is basically at the end a mesh in the introdos and a mesh for the extrodos. So then we have these two meshes. So we can use them to build a parametric tunnel in Grasshopper. So we have a component to build the different tunnel sections, which takes basically a template of the theoretical section and the alignments we computed before, and then stations for start and end, and some other parameters to tweak stuff around. And notice that here at the top, you see the extrodus is kind of wavy because it's following that regression surface from the extrodos, and for the introdos you would see the same thing, and we will see that in detail when we see the demo part. I will cut a section through and I will show you that it's actually snapping to the introdos mesh and to the extrodos as well. And then we can compute we can model different sections of the tunnel. So the mouse is moving. The traditional sections of the tunnel, but also bypasses, and I'm not sure how this is called in English. So it's the cut entrance of the tunnel. So then we have niches and even weird ventilation shafts. You can model pretty much anything. These are just done in Grasshopper with parametric tools, and they follow the alignment of the tunnel as well. And then we can model the road as well. The mouse keeps moving the slides, which is weird. Okay, let me go back. Okay, I won't use the mouse. I won't touch it. Okay, so as you can see, you can model the road. We can model the road as well, and then the road is cut with the surface of the introdos, so that in the construction documents they talk to each other, and also in the 3D model. All right, so this is basically the typological section that we build. So we start from the theoretical section, which is just a CAD template drawn in 2D, and then that is placed along the alignments. And you could do a traditional loft to build a new tunnel geometry because the section is constant. You could also do a sweep probably in that case. In case of an existing tunnel, you can't do a sweep because the section is not constant. So it's sort of like a bridge, but even with more complexities. So as I said, we have a mesh at the introdos, a mesh at the extrodos. The one at the introdos comes from the survey. The one at the extrodos comes from the geological reconstruction. But they're just two meshes. And then the grasshopper model basically goes and computes where those meshes are relative to the theoretical section and deforms the theoretical section so that it snaps both to the inside, the introdos and the extrodos, and we get the actual real thicknesses of the model. Of course, we are sure about the introdos, not about the extrodos. That's just an hypothesis. And for the reversed arch at the bottom, we keep the geometry that was in the theoretical section, but we have the ability to move it up or down. Of course, it scales horizontally slightly because the arch, the crown, changes shape slightly because it adheres to the introdos mesh. But also you can move up and down the reverse so that it matches with data you could have from surveys from boreholes done in the roads. Okay, so this is the basic idea behind the component. And this is useful because, of course, you could see that in the theoretical section. This is an example. You could have the as-built introdos. The as-built is the theoretical one. It's the red dashed surface. That's what you would do, in a new tunnel. Probably you have the theoretical section, but reality is different. And if we consider that as the reality to start to design, we would make mistakes of several centimeters, which could add up in the calculations of volumes, which could create problems then when you're in the site. All right, so then, okay, the road, the approach to model the road is we have characteristic lines, so lines that go in the longitudinal direction in the tunnel, and we use them basically with lofts to build a section. We have sections, you have points that cut through these lines, and then you just project the line on the reverse, and you get these solids. So you can split the different parts of the road, and this is the final model. And then we can use as well some annotations tools to compute the different traffic volumes, so we can check that everything is right. Of course, we can do this. The example I showed today are all of rebuilding the existing tunnel. We then model the intervention as well, which is just basically a new tunnel. So it's easier to model because it's a perfect theoretical section that you just extrude in. And then we can do the check of the traffic volumes for that as well. And we can extract sections and everything, but we will not deal with construction documents today, as that is not particularly interesting. The last thing we will show, again, in the demo section that will start shortly, is then when we have this 3D model in Rhino, we want to create an IFC model out of it. So to do that, we developed a couple of components that use IFC OpenShell that take the mesh, that convert the geometries to mesh, take the properties that are saved in the Rhino file or that you can input directly in the Grasshopper canvas, and write a custom, like a native IFC file where we can control all the parameters, the hierarchy of the file, and psets and QTOs that you may need. All right, so let me go to the practical demo. So we will start with the first file, I guess the survey. So we'll now go back to the beginning of the presentation in terms of content. So here's what we have at the start. Let me minimize this. Okay, this mesh we don't have, so let me hide it for a second. And this one as well. Okay, so this is what we start from. Let me close Grasshopper as well. Okay, so these are just lines that come from the survey, and what's most interesting for us is these red curves that may have different resolutions. In this case, it's not too high. It may have more points, less points. Each arch has a different amount of points, and as you can see here. And also the arcs are not oriented along the alignment because they're just random curves in a CAD file. So we have this Grasshopper tool, which takes this tunnel arches, and then the survey to alignment component just takes a rough rough alignments. So this rough alignment, it's just, let me go to the top view, let me show that. Okay, so the rough alignment is really a line. It's just telling it, well, the tunnel is going pretty much from here to there. It's just used to orient and decide which section is like further or like the order along the alignment. And then we can order them. So we have the ordered sections, which are also projected on the planes perpendicular to the calculated alignments, and we get an alignment curve. So the alignment curve is like this green polyline that you can see at the top, and these vertical planes, or actually perpendicular planes to the alignments, are the planes on which the survey sections were, but since the survey section maybe it's slightly off plane, it was reprojected on the plane to be sure that it's flat. And then we can use these alignments. As I said, we can split it in two parts. One is the horizontal alignment, which is just, let me show that, which is just a curve here. I can't see it here actually. Let me see. Okay, there. So it's just a 3D polyline. My scroll wheel is not working very well. Okay, it's just the 3D polyline projected on the ground. That's the horizontal alignment. And then we have the vertical alignment, which instead is kind of a gimmick because there's not really a profile view in Rhino. So to work around it, we just used, basically, this is the, like you could imagine the x-axis as being the stations along the alignments, the vertical axis as being the elevation, and this is just the line that represents the profile. So then we can take these two polylines and join them together, and that's the 3D polyline that makes up the alignment. So let's go back to the tunnel. Okay, fine. And then you can take this horizontal and vertical alignments, and we have this component which just extracts the land XML file, which is just any XML file that you could create in Civil 3D in the same way. And you can also import this in Civil 3D as well if you're using that or any other tool that reads this kind of file. And indeed, you see you have the elevation points taken from the profile here, and the horizontal alignment taken with coordinates on the flat ground. All right. So second part is we take this the arcs that we used to extract the alignments, and now since we have the alignment, they are ordered along the alignment, so we can also do a loft, and this is basically what this component is doing. So it's taking a loft with a certain set resolution. Let's maybe change it so that you can see it update. There it is. So 20 or like 40, that updates the number of segments that are used to approximate the mesh. And this generates an approximated mesh. We will not use this to snap the tunnel, but to clean a point cloud. So we have a point cloud. As you see, the default point cloud is quite dirty. This is Cloud Compare, but you could use any tool you like. This is open source. Yeah, I believe it's open source and it's free anyway. So you can use it for commercial use. And yeah, this is just the point cloud with also the context, so it's kind of dirty. So we can subsample it, so it has a little less points, and then we can simplify the mesh. And the way we do that is, sorry, this is the simplified mesh that we created in Grasshopper. So it's the one we created by lofting the arcs. And then we can take this, we can take the original cloud, and we can check the distance between each point and the mesh. And by doing that, we can filter out only the part of the mesh which is interesting to us, which is the introdos. And then this is the filtered one, and then we can just compute the normals and use Poisson reconstruction to build a mesh out of it. And this is just the mesh of the introdos, which is the one which we will take and re-import in Grasshopper. So we just, in Rhino anyway, we saved it as a PLY, and then you have it here. I hid that. I've hidden them before, so there it is. So the one in black, it's the simplified mesh, and the one at the top instead is taken from the point cloud, and they are not, of course, perfectly touching, at least. I mean, they are in the location of the arches, because those were extracted from point cloud at the beginning. But between the arches, instead of just connecting with straight lines, we also have the information about how the tunnel is shaped. All right, so this is all about the survey part. Now we can go to the modeling of the tunnel. I guess it's this one. Yes. Okay. So we will get to this stage. So I will just show the introdos snapping today. So the extrodos is just going to be a simple extrusion, but like still demonstrates the point. So let me open up that one here. All right, so we have our alignment file, which we created before. We can import the alignment from XML, and you can also visualize it in 3D here. Okay, it's the same one we created in the other file, and it doesn't support only polylines, but also like curves, parabolic arcs, real arcs, and colloids. So you can do pretty much whatever you want. And then we have to create our tunnel. So this is the basic component we have. Let me just show. Like, this is the components we created. The one to create the alignments are here, and we have a bunch of tunneling and road modeling. So we are using this for survey tunnel modeling. So to do that, we get the horizontal and the vertical alignments, which is just taken from the XML file. And then we get the templates I was mentioning before. So let me turn on the preview and zoom to them. So a template is really nothing more than a couple of polylines, one for the introdos, one for the extrodos. And in case you use another component, which is this one, I will not show it today, but it's like I can discuss it. So the standard tunnel modeler, that would be like a new tunnel or a design intervention. You would also have some lining, so you can differentiate between the walls and the crown and the reverse. In case of an existing tunnel, we do not split between the different lining components. We just have an introdos and an extrodos line. All right. But then we have the begin and an end station. So let me show this component again. So in this case, we have a component that is going from 0 to 15 meters for our alignment. And then in this case, we also have a portal, which is just cut. So we have also a polyline. Actually, let me disable this. So you can see this is the default piece without cutting it. So from 0 to 15 meters. And then we can specify there an amount of meters where you want to put a cut plane, and the cut plane angle, 45 degrees in this case. And you have this slanted cut here. We did the same thing on the other side. So this is the same on the other side for the other piece of tunnel. And then I just did a single section. This is not an existing tunnel, like it's just an example. It's not it doesn't exist in real life. So this is just a middle section with a constant section, but I will use this one to show you the snapping to the mesh. So let me hide maybe this and this. So the two portals, and let me focus to this, and let me also reduce the length. So I will just go to 30 meters. So it's shorter and it's easier to see, maybe even more. Let's go maybe 20, 25, maybe 20. Okay, yeah, like that. And then I will put the side view. Actually, let me zoom in. There. Okay, I will go to a side view here, and then I will switch off the mesh. So this is this is not mesh. This is the mesh that we've imported from Cloud Compare. So let me preview it off. Okay, and then I will just disable it now. And if you focus on, let me see if it's long enough, this part, enable. Yeah. Let's take a longer section so you can see it better, because it depends on the bits of tunnel you section. It may be more or less deformed. So let me turn it off. yeah, like if you focus like maybe at this on this right wall, you will see that it moves when I enable it. So now it's just a theoretical section. If I enable the mesh, it will, you see, shrink a little because it's snapped to the existing mesh, and then it modeled the reverse accordingly, because like if the arch it's not as large, the reverse will adapt to it as well. And instead, for the extras, in this case, we're leaving it as it is from the theoretical section. You could do the same thing if you provide the extras target mesh to the component. It will do the same thing. All right, so I guess that was it for the modeling of this the existing tunnel. So let's go to the next example, which is let me see, the road. Yeah, the road example. Okay, here. So for the road, what do we have as a start? I lost that. Okay. So we have this. Let me hide the result. And maybe even turn off Grasshopper. They're zooming the way. I can't whatever. That's right. Okay. Let me close it for a second. Okay, so these are just the characteristic lines that I was mentioning. So this is the tunnel, and these are just the lines which define the white lines which separate the lanes, and also the black lines which identify the sidewalk, and they're going all the way through the tunnel. In this case, we have the same number of tunnels, so a constant road section throughout the whole tunnel. If you have multiple, you can just split them up and do them. In this example, I just have one single section, so it's easier to show. Let me open back up Grasshopper. Okay, so here, so we are importing the alignment as we did before. So we are using the same alignment as the tunnel, not to model the shape, because the shape of the road depends on the characteristic lines. We're just using the alignment to get the stations with the same numbering as for the road, just to say that if the road goes between like 10 meters and 15 meters, they are the same 10 meters and 15 meters of the tunnel. If you follow a different path for the alignment of the road, they wouldn't match. So that's why we're using the alignment of the tunnel. But of course, you can generate and import as well the alignment of the road, and they would be slightly different, but you can use them. Okay, so then we're getting just all the lines from their layers here. Okay, in order between, like, from left to right, or from right to left, in this case from left to right. And then I'm just taking, well, I'll show you, but I'm just taking the introduced surface. Where did I get this? I didn't show it here. So in the file we were using before, you can, like, this component gives you a bunch of outputs, which I haven't shown, so I will do here. So it gives you control planes. In this case, we are using just 3 lofting sections, because the way it works is basically it creates, like, as I said in the slide part, it takes the template and puts it attached to the alignment, and then it creates a couple of sections, and depending on how many you want, you set up in this increment distance. Let's maybe say that we want one every 1 meter. So in this case, every 1 meter we have a section. So every 1 meter we have a plane. We have an extrudos curve. We have an introduced curve here, and then you just loft through them, and you have your section, and then you have the I guess the extrudos surface there. And the one we are using in the other file, the introduced surface, which is a BREP, which we can use to cut the road solid so that it snaps perfectly to the volume of the tunnel. So let's go back to the road. Where's the road now? Here. So this is just the introduced BREP surface. Okay. And then let me switch it off because it's distracting. Okay. And then we have this component which just builds the road. So as you can see, maybe from the icon, it basically goes and places control planes, like plane. Okay. Control planes along the alignment, again, at a certain increment distance that you set, or you can specify specific stations you want, maybe taken from some notable points that you want to section through, or you can use the horizontal and vertical kinks of the alignments to place additional sections, like maybe Civil 3D does. And then, you have all these planes, you cut all the characteristic lines with these planes, then you build polyline, and then with the polyline, you just loft through them and you have the surface of the road. And then you can also intersect it with the target surface, which is just the introduction of the tunnel we were talking about before. And in that case, you have a road solid here that I just baked already in the scene. So let me do that again. Solid. No, I did not bake it, whatever. You can see it as a preview. We can bake it maybe now. Let's do that just because. Okay. And there you can see we have the surface of the road. Let me bake it, maybe walk in the tunnel so you can see it a little better. Left click. Okay, there. So there you can see we have our tunnel modeled from survey and the road which is going in it. Let me maybe cut a clipping plane through as well, so you can see it even better. Clipping plane, vertical, right there. Okay, and then we can maybe cut through, and there you can see the reason it's slightly glazed graphically is because we are modeling at 50,000 meters from the origin, which is not advised, but we are risky people here. Okay, and you can see the road is just cut with the introduction of the tunnel, and you can, as I said, walk through it, and you will see the road follows along, and it's perfectly integrated in the tunnel. All right. So the last bit, I guess, of the demo is where it is, export to IFC. Here it is. Okay, so I will just export the tunnel. You could export the road as well. So what do we do to export IFC? We have another set of components here to create an IFC file, to create the hierarchy of the IFC file, create an object, and pieces and QTOs and styles, or even query an imported IFC. So you could import like IFC read and query by type, query by GUID, query by ID, and do a bunch of things. This is based on IFC OpenShell in Rhino and Grasshopper. So we're just importing with, I believe it's human. Yeah, let me just check. Yeah, with the human plugin, I'm importing from another file the solids that we generated for the tunnel, and I converted them to mesh because at the moment this plugin we developed has just it just supports meshes. But for IFC, like most commercial tools, don't actually go through actually modeling them with implicit geometry. They do just meshes, but we will implement the proper extruded solids. In this case, there I believe extruded area solids or stuff like that in the IFC spec for IFC 4.3. But at the moment, we just have meshes and we exported them to IFC 4.3. So there's no alignment. So it's a work in progress, but it still works pretty well. So we have these three solid objects as meshes now. So let's go through the plugin. So we create an IFC model. This is just an IFC model stored in computer RAM version, as I said, IFC 4, the default. Then we create a project called Hopper project by default. We create a context, a site. We create a building. As I said, is IFC 4, not 4.3. So we don't have the road and the other facilities. We're just using a building. And we then have a building story. We will use the building stories like as a longitudinal division. So we just called it portal in, middle, and out. This is just so that in the viewer, when you open it up, then you have some hierarchical structure that you can go through. Then we define two colors, two materials, one for the portals and one for the middle section with this style component. And then we have this IFC object. This takes in, well, the model is just being passed between each component so that it's updated each time. All right, then you have a name that we call the porcelain solid. The context is the one we created at the beginning. The class we just decided is an IFC wall. The mesh is the mesh we took from the model. And the style ID is just the ID, like the step ID of the style we created here. And then this creates an object. And we created 3 objects. You could also use lists and trees and have one component. I just split it in 3, so it's clearer in this example. And then after this, we just add the sample p sets to object number 1, and then a sample QTO to object number 2. All right. So in case of the p set, we just have 2 random properties, prop 1, prop 2, with value 1 and value 2. You could put whatever you want. And then in the QTO, we are computing the volume. So we are taking the volume of the geometry, and then we are converting it to a number, and we are plugging in the value. So we will see that, we can see it here already, 16,000 cubic meters. And then we'll have the quantity properly set with the proper quantity since we set its volume. In the IFC viewer, we will use Beam Vision, and then we can just export the file. So let me go to the files here, and we just created this file, IFC export. All right, and you can see this is the same model that we had in Rhino, and but it's an IFC. It's a mesh, as I was mentioning. I did not export the road, but you could do whatever object. And we have the hierarchical structure. We used stories as a fake longitudinal subdivision. And then we've said that object 1 had a p set, and indeed here's a p set, and object 2 had a QTO, and indeed we have a QTO with the proper unit of measurement. It's a volume 16,000 cubic meters, whatever. Yeah, I believe I showed everything I wanted to show today. So I'm open to questions or any curiosity. And just to mention, before questions, the plugins I showed, this, damn it, I have all the Zoom interface in front of it. Okay. So this TECNESYSTRA one, it's for internal use only, so we don't share this. The IFC upper shell one, instead, we're planning to release it open source pretty soon. I can't give you a date yet, but the technical development of the initial version is done. So we're going through some clearance, but we are planning to release this export and import of IFC to the public pretty soon. So stay tuned for that. All right, I guess.
Thank you so much, Mattia. It has been really great, really clear and easy to follow the explanation. I think the workflow is also really clean, and you have everything very well organized. There are some questions in the chat, but yeah, people
All right,
can keep asking them. Yeah, the first one was at the beginning of the presentation, because Alessio, when you were showing the PowerPoint, and Alessio Bianchini was asking, was saying that it wasn't clear how you define the external surface.
Yeah, right. I didn't mention it too much because it's not done in Rhino and Grasshopper. But the point is, let me just reshare these 2 slides. Basically, we have Borel data. So Borel data is just, let me see it. This mouse. Okay, it's just an Excel spreadsheet with like for each line you have a Borel, and then in the columns you have the different thicknesses of the different materials. So you find concrete, then you find a void, then you find a rock, and whatever, and you have a bunch of them, and you have the position. So the stations, lateral and longitudinal station, and the angle at which they were. Well, actually not the angle, because from the stations you get the angle. So from that you have the data about the different layers, and so then we take that Excel file, we read it in Grasshopper, and we display, like, it's not very big, but you can maybe see if I can zoom in better. Okay,
but
here.
Sorry, are you sharing?
I'm not sharing the screen. Yeah,
okay,
right.
no,
Sorry,
no.
I will share. I mean, Where's the share? Sorry, here. Okay. So as I was mentioning, I mean, the Excel file is pretty self-explanatory. I wasn't showing it anyway. Then we import it in Grasshopper with this component, like a read Excel basically. And then this just places those layers as cylinders. It attaches them to the introdos. So the introdos, we got that from the survey. And then by positioning these in 3D, we can also get all the 3D coordinates and points of the different layer separations and vectors that define the directions. And then not in Grasshopper, but in a specialized software called Leapfrog, which is from Sequent. It's not in Grasshopper, it's done in Leapfrog. You can take these points and vector directions, and it generates for you a surface, basically, which is just a mesh, which is an approximation of what the extrudos may be, given the position of the concrete you found by performing borals in the tunnel. So that's the idea, to rebuild the extrudos. Of course, it's just an hypothesis, which is not necessarily perfect, but it's the best we can do with the data we have. So that's the idea. You could do the same thing. It's just using RBF functions. So I'll just stop sharing for a second. Mm-hmm. I'll just tell you the name of the script you can use if you want to do it in Python. You can do it with a library called GemPy. So if you look up on Google GemPy, it uses the same algorithm called FastRBF. And it takes points and vector directions and builds these surfaces for you. So you can use that. If you know how to code, you could implement in Grasshopper through Python that kind of same approach. So yeah.
Okay, thank you so much. Yeah, and the next one was from Kartik, I see here. He asks, how do you develop the Grasshopper custom components, and what language do you use to develop them?
Okay, so at the moment, they're a mixture of Python scripts and clusters, so they're not coded. We are converting them to code to a code base in Python, compiled through the script editor. The Rhino 8 now has a built-in compiler. You can write the components either in C# or in Python and convert them, or you could as well build a native component outside in C#. But since we're using a couple of libraries which are just in Python for creating clotoids, this one for GemPy, IFC OpenShell, we have a bunch of libraries which are not available in C#. That's why we're using Python for compatibility. And so most components at the moment are a mixture of scripts and clusters. We're converting them to an actual plugin, compiled plugin. So that's the answer. Instead, IFC OpenShell, the one for exporting IFC, that is already all converted to a Python compiled component plugin with the script editor. So the one which we're planning to put public, that is already a plugin.
Okay, great. I think it answers the question perfectly. The next one is if you can manage drastic changes in the tunnel profile with the Grasshopper definition, for example, lay by niches or confluence covers.
I'm not sure I understand the question, but
yeah.
If the question is, can we model niches and let me share the screen again. So let me share back here. So yes, we can model niches and complex geometries. I'm not sure if you mean this or which other types of complex changes, radical changes, but yes, these are supported. The way we do it is we just model the tunnel without them, and then you just attach it afterwards. So those are not modeled by survey, they are, but they're manually modeled from the measurements. And you create a Grasshopper. There's a Grasshopper definition that creates them and attaches them to the tunnel, and then you use it's basically like a small tunnel. So you also get from the same component that create the tunnel the intrados volume, the extrados volume. So you can use those with solid Boolean operations to cut through the lining, and you have that parametrically as well. which is quite useful to have everything parametrically, because then if you change the alignment, all the niches and everything follows along because it's parametrically modeled. So yes, you can model those as well. They are kind of a special use of the basic tunnel modeling tunneling model component. So yes, you can do that, and the same for the bypass. So it's just another tunnel stuck to it and cut with Boolean operations.
Okay, perfect. Let me check what's the next one. Yeah, Bernhard asks, how did you get the cross sections from the point cloud?
Okay, in this case, we did not get it. The contractor did it, like a topographer, but you can do it in Cloud Compare. Like not in this example, but in other cases, we did it ourselves. So with Cloud Compare, there's a tool. I mean, you can look it up online, but I believe it's the tracer polyline. No, it's this one. Extract cloud section along polylines or unfold the cloud along the polyline. So this tool basically does what you want. You have to tweak the parameters in a clever way, but if you have a clean point cloud, so after cleaning the point cloud, when it's already filtered, then you can extract that. So of course, this is limiting because we cleaned the polyline, the point cloud by having the sections already. That's not usually a problem we have because we get those from the contractor, but the contractor does it in a similar way. I mean, they cut through the polyline, through the point cloud, and then they clean it up a little manually so that they are cleaner. But that's the answer. I'm also not sharing the screen, but I wasn't showing anything specific. Okay. Here. So you can use Cloud Compare, and this is the tool to do it. I have to zoom in the middle. Yeah, here. This one is extract cloud section along polylines. This is the tool.
Yeah, first another question from Bernhard now. How did you recreate the 3D polyline of the alignment?
That one is done in Grasshopper. So we have this survey to alignment component, and the way you do it, like logically, is let me hide this. Okay, let me hide this as well. Okay, so you have all these arches, and what you would do manually is you would go through and look up what is the topmost point of the arch, not necessarily like the actual point, but maybe in this case we use a NURBS reconstruction, and then we take the top point of the NURB because it's a better approximation. And then after you have the top point, you connect all the points in succession, and that's just the alignment. This script just does automatically what I said now. So instead of doing it manually, it's a script that does it for you. It just runs in a couple of milliseconds. So that's the answer. Okay,
great. And the next one asks, have you imported your IFC export into Revit? If yes, how did it look?
We did import it to Revit with the IFC, not because of the IFC, because of the Revit. How Revit works, it's like not particularly usable. I mean, you can import it as a visualization, as a proxy, but you can't work on it. That's because of how IFC works. You could use, for a better workflow, the Rhino Inside Revit plugin. So if you use that, you can take the geometries from a Grasshopper and custom, basically bake them direct to Revit. In that case, that is a much better workflow, and what you get are native Revit families. So if you have to go to Revit, I would advise to follow Rhino Inside Revit, not really to use IFC, unless you just want a proxy to visualize. In that case, you can import it as any other IFC.
Yeah, also I was checking another one that is related from Piero. He asks, what is the Grasshopper add-on that you use for IFC export? If you can
explain. So one way, we developed it internally. It's called, it has just a funny name, IFC OpenShell, because it's based on IFC OpenShell. So it's just a bunch of components that use IFC OpenShell underneath, and we're just using the library. So we implemented ourselves. And as I said, we're planning to release this plugin open source and with GPL3. And so you'll be able to use it pretty soon. I can't give you a date, but I can say that we will release it. So follow along and you'll have it as well.
Okay. And the other one was if you have faced the necessity to extract from the models created in Rhino the drawings for the WG or PDF with complete
Yeah.
design, including dimension views.
Yeah, we did that. We did. I didn't show it today, but you can do it. Just I give you some hints about how you can approach the problem.
Mm-hmm.
Let me share the screen maybe again. Okay, here. So the idea is, let me say here, okay. We have our 3D object. We have planes. You can define planes in the scene, and then you can just use, let me see. You have two ways of doing it. If you just need a section, you can just do intersect the plane, where it is, no, BREP, BREP plane, and then you can use that plane intersected with the object that creates a 3D section, like a 2D section in 3D space. And then you can use orient, which is just a component which takes the geometry in 3D, a source, which is just a plane used to cut the solid object, and a target, which is the flat plane of the CAD, like the XY plane. And in that case, you would get all the surfaces, all the sections cut on the ground. And you can do that for the sections. Or if you want also like the background, let's call it that way, you have make 2D, and you can use you can do this a similar thing to that. So that's for sections. Instead, for profiles and plan views, you have to do a trick to model them, because there is no way to cut with the non-flat plane in Rhino, and you can't do it in Revit as well. So the way you do it, since everything we modeled is parametric, you can take the Grasshopper definition, build another one, exact copy of it. You don't have to actually copy it. You can import stuff or whatever. Conceptually, you can make a copy. And then if you just take an alignment, which is a fake alignment, and it's made up of the real profile, and an alignment which, instead of like curving, it has the same length, but it's just a straight line. All the components will take the tunnel, rebuild it parametrically flat, and then you can cut it with the flat plane, and that you can do a profile. And with the plan view, you do the opposite. So you just delete the profile and you get only the plan view, and then you cut it with an horizontal plane, and you can do all the sections. And we also did, like, when you cut the surface, if you also put proxy lines in it, like the characteristic lines of the road, for instance, you can also compute dimensions, place them, bake them in the Rhino scene, and then when you move them to AutoCAD, they will work. So the only tricky thing is annotations, but they are translated as well. So yes, you can do that, and we did that for a couple of tunnels. So yes, absolutely. If the client needs CAD drawings from it, yes, that's what we do. Otherwise, you go to Revit, you go to different targets, depending on the client requirements, the project requirements.
Great. I think the last one is from Joseph. Can we compare the lofted geometry to the point cloud in Rhino Grasshopper to ensure a predefined accuracy?
I mean, visually, of course. You can also do it computationally. Yeah, you would need to. It's not particularly efficient because point clouds are very heavy. So instead of doing it in Grasshopper, I probably would advise to take the introduced geometry you got from Rhino, put it back in Cloud Compare, and then do the mesh to cloud distance, and then use that to compute this. But yes, theoretically, you could do it in Python. In Grasshopper as well. It's just not efficient because a lot of points.
Yeah, exactly. Well, there are many other messages saying thank you, that it has been very nice presentation, very interesting work. So thank you so much again, Mattia. I think it has been really helpful for many people, and for me too. It's really interesting to see the workflow. So I'm not sure if you want to add anything.
No, I guess thanks to everyone that followed me, and yeah, see you around.
Yeah, okay, thank you so much. As I said at the beginning, it has been recorded, so I will upload it tomorrow morning, so you can check it again if necessary. Thank you so much. Have a nice afternoon, everyone. Bye bye.
Bye.